cool thing about simple continued fractions is they provide a way to solve some Diophantine equations. We plan to cover this in a series of videos. This video is an introduction. We'll take a look at the equations we have planned for future videos, and we'll say a few things about Diophantine equations. Let's get started. We want to get to the subjects of future videos quickly, but there are two things to note about Diophantine equations. They have one or more unknowns or variables. Usually there are at least two. The distinguishing thing about Diophantine equations, though, is that we are only interested in solutions that are integers. Please keep that in mind as we discuss some equations that we will be covering in future videos. We will look at solving linear equations. The equation will be in this form: ax plus by equals c. There are two unknowns, x and y, and three constants, a, b, and c. This equation draws a straight line. In coming videos, we'll see how to use simple continued fractions to find points on the line where both x and y are integers. Another subject is generating Pythagorean triples. We'll use this blackboard for a quick review of what we mean by this. If we have a right triangle and the lengths of the sides are a, b, and c, the theorem of Pythagoras tells us that a squared plus b squared equals c squared. When a combination of a, b, and c satisfy this equation and they are all integers, we call a combination a Pythagorean triple. An example of a Pythagorean triple is when the sides are 3, 4, and 5. 3 squared plus 4 squared equals 5 squared. So, the equation is a squared plus b squared equals c squared. There are three unknowns, a, b, and c, the sides of a right triangle. In coming videos, we'll see how to use simple continued fractions to generate Pythagorean triples. In other words, integers a, b, and c that satisfy the equation. The next subject is decomposing Pythagorean primes. This also involves right triangles, and just like before, we can label the sides a, b, and c. This time, though, a and b are integers, but the hypotenuse c is not an integer. Instead, c is the square root of a prime number, which will denote p. The theorem of Pythagoras holds, so we can still write a squared plus b squared equals c squared. C is the square root of p, so when we square it, c squared equals p. Not every prime number works in this equation, but infinitely many do. The square root of 5 is one of them. The combination of a, b, c is 1, 2, and square root of 5. 1 squared plus 2 squared equals 5. So, the equation is a squared plus b squared equals p. There are two unknowns, a and b. These are the lengths of the two shorter sides of the right triangle. Let's get the blackboard out of the way. And there's one constant, p, which is a prime number, and it's also the square of the length of the hypotenuse. In coming videos, we'll see how to identify which primes are Pythagorean and to use simple continued fractions to find integer lengths a and b. This is what we mean by decomposing the prime. The remaining subject that's planned is solving Pell's equation. It looks like this: x squared minus d times y squared equals 1. There are two unknowns, x and y, and one constant d, which is a positive integer that is not a perfect square. In coming videos, we'll see how to find integers x and y that solve this equation. Those are the subjects we have planned. Simple continued fractions provide a way, not the way, but a way, to find solutions to these equations. Now let's note a few more things about Diophantine equations. It's actually a really broad set of equations. It's acceptable to multiply the unknowns times each other. We don't do that in any of the equations we just discussed, but it's acceptable. And it's acceptable to have higher powers. In our set of equations, the highest power we have is 2, but Diophantine equations can have higher powers. Also, the exponent or exponents can be unknown, something you try to solve for. That also doesn't appear in any of the equations we just discussed. Whatever the equation might be, though, it is always the case that we seek solutions that are integers. This is non-negotiable. Diophantine equations can be difficult or even impossible to solve. More unknowns, higher powers, and exponents as unknowns can quickly make equations difficult to solve or impossible to solve. There's a famous example, Fermat's last theorem, which goes like this. We have this equation: a to the n plus b to the n equals c to the n. It has four unknowns, a, b, c, and n. Fermat's last theorem says there are no integer solutions when a, b, and c are positive and n is greater than 2. It is remarkable how quickly the difficulty goes up as n increases. When n equals 1, the equation in the theorem becomes a case of this equation. If n equals 2, his equation is the theorem of Pythagoras, which has infinite solutions. But if n equals 3, there are no solutions. Fermat proposed this theorem back in 1637, and it was proven by Andrew Wiles over 3.5 centuries later in 1994. There's a documentary about Andrew Wiles' quest for the proof. The math is beyond what I could hope to grasp, and most people too, but the documentary is very good. It is highly acclaimed. These equations over here though, which will be the subject of coming videos, only require knowledge of basic algebra and little geometry. To recap, we discussed some Diophantine equations that will be the subjects of videos that are coming, and we made a few notes about Diophantine equations. That's all for now.